Okay, so we begin lecture 39 now, in which we will talk about point defect concentration and the line defects. So, what we talked in the last lecture was about that materials in reality they have various defects, and depending upon the nature of defect they can be classified in three categories: point defects, which are 0-dimensional defects; line defects, which we have not talked about yet; and 2-dimensional defects, which are line defects are 1-dimensional defects, and 2-dimensional defects are surfaces, basically grain boundaries, twin boundaries, which we will talk in perhaps this lecture or next lecture. So, what we will do is that now we have seen that there are point defects such as you have vacancies, you have interstitials, you have so this could be substitutional, you can have substitutional impurities. Sorry, interstitial cannot be substitutional. So, you can have interstitials, you can have substitutional atoms, you can have paired defects, typically in ionic solids, such as Frenkel and Schottky. So, these are some defects that could be present in the vacancies in various materials. Vacancies, for example, in metals, just the metal vacancy. In case of ionic solids, it could be cation vacancy, it could be an ion vacancy. Interstitial could be cation interstitial or anion interstitial. Substitutional again could be cation or anion substitutional, depending upon what you put in the lattice. Now, what we will do is that we will do a simple analysis to work out what is the analysis of defect concentration. All right. So, basically what we do is that when we introduce a vacancy in the system, it leads to change in the thermodynamic parameters such as entropy, okay, entropy and enthalpy. So, let us first work out what is the change in free energy, that is delta G upon formation of vacancies. Okay. Now, if you form a vacancy, which means it must cost energy because you are removing an atom. Let us say the energy of formation of a vacancy is equal to delta small gf per vacancy. Okay. Now, the change in the free energy, corresponding change in the free energy, which is G minus G naught. G naught is the equilibrium free energy when you did not have any vacancy. So, this change in the free energy, which is delta G, this can be related to, now delta G is equal to delta H minus T delta S. Delta H is number of vacancies multiplied by the heat of formation, enthalpy of formation of vacancies, which is delta Gf, minus T delta S, and this delta S happens to be change in the configurational entropy. So, when you introduce vacancies in a material, predominantly you are changing the configurational entropy, because now you have, since you have one vacant place, the atoms can be put into various configurations. So, we need to work out what is the configurational entropy that happens upon the change in the configuration entropy that happens upon introducing a vacancy. So, this delta SC is basically change in the entropy, and this is basically positive in nature, as we will see. So, delta SC is equal to small k ln W, where k is the Boltzmann constant, and W is the number of ways in which atoms can now be arranged. Okay. So, number of ways in which atomic configurations can be created after you introduce a vacancy, right, and this happens to be small k ln n exclamation mark, which is factorial n divided by factorial n into small n minus n factorial n, where capital N is the number of lattice sites, not number of atoms, number of lattice sites, because number of atoms have now reduced. Okay. And small n is the vacancy concentration. So, these are basically, so capital N is the total number of sites, n minus n is the now number of remaining atoms, right, because small n is the number of vacancies. So, basically these many number of atoms have now to be configured on the n lattice sites. So, to solve this equation, we make a approximation which is called as Stirling's approximation, which is called as ln n factorial to be equal to n ln n minus capital N, and likewise you can write small n is equal to small n ln n minus small n. So, if you apply this approximation to the above equation, what you find is that delta SC is equal to small k into capital L ln n minus n minus n ln n minus n minus of small n ln n. This is what you will get after you apply this approximation, and then you substitute of course in delta G. Delta G will be equal to n delta Gf minus of T delta SC, and for delta SC you will introduce this. Now, if vacancies were equilibrium defect, which means the free energy must become minimum at a certain concentration, right. So, if you plot the free energy as a function of vacancy concentration, the free energy G, so this is let us say 0, the free energy must become minimum at certain concentration. This is concentration n equilibrium, and this should show a minima, right. This is delta G min. If it is not minimum, then it is not a stable defect, right. So, when you introduce vacancies, and if vacancies are indeed stable defects, that means delta G should show a minimum at certain concentration, which means del of delta G by del n is 0 at n is equal to n equilibrium, and since n is much larger than small n, I can say n minus n is equal to capital N. So, if I do this now, differentiate the above equation which I have showed earlier and apply this condition, what we will get is n equilibrium is equal to capital N multiplied by exponential minus of delta Gf divided by small kt. This is the equilibrium concentration of vacancies that we calculate, which means now what this expression shows, that higher the energy of formation of vacancy, smaller will be the vacancy concentration. higher the temperature is, larger the vacancy concentration will be, lower the temperature is, smaller the vacancy concentration will be. And that is why different materials show different vacancy concentration. For example, if you calculate a difference between aluminum and nickel, at 0 Kelvin, of course both of them will have 0, okay. At 300 Kelvin, aluminum will show you 1.45 into 10 to the power minus 12 fraction of vacancies, okay. So this is basically n divided by n, okay, and this happens to be 5.59 into 10 to the power minus 30, and at 900 Kelvin this happens to be 1.12 into 10 to the power minus 4, this happens to be 1.78 10 to the power minus 10. So you can see that as the temperature is increasing, there is an exponential increase, but there is a difference between aluminum and nickel. Aluminum has a vacancy concentration which is far higher as compared to nickel, because nickel is a high temperature material, aluminum is a low temperature material. The bond energy of nickel is higher as compared to aluminum. As a result, the energy which is required to form a vacancy in aluminum is lower as compared to energy that is required to form a vacancy in nickel. So delta GF for nickel would be larger than delta GF for aluminum, which is dependent upon the bond energy of the two materials. So this is basically the equilibrium vacancy concentration calculation. For Schottky defects, ionic defects, the equation will change a little bit. So since you have vacancy, so delta V, let us say vacancy of A is equal to vacancy of O, let us say for a AO solid, okay. So this would be 2 minus, this would be 2 plus, and this is basically total number of sites n exponential of minus delta HF, which is the free energy, which is the enthalpy of formation of vacancy, divided by 2 kT. So here you have this factor of 2 that comes in the denominator for ionic solids, but the relations are similar, all right. So this is about the point defects discussion, that you have point defects such as vacancies and interstitials, and point defects are basically stable defects, they are equilibrium defects, and free energy is minimum at a certain concentration at a given temperature, and that their concentration increases as a function of temperature. So as you increase the temperature, they become more in number exponentially, okay. So now let us discuss the second category of defects, which is called as line defects. Or 1D defects. Now these are in the language of material scientists, these are called as dislocations, okay. There are two kinds of dislocations that we find in materials primarily. First is called as edge dislocation, second is called as screw dislocation. Edge dislocation essentially is an extra row of atoms in the material. So you have a structure like this, which is a perfect structure, okay. Now what we do here is we remove some of the atoms. So we remove these two atoms, these atoms, let us say. So what happens in this case now, this structure will now slightly, because you have created an extra row of atoms in between which does not completely go through the material, as a result it will create some distortion. So you will have distortion like this, and then in between you will have these atoms. So this is an extra row of atom. So, this extra row of atoms has created a strain in the lattice. This part has expanded and this part has contracted. As a result, this part will be under tension and this part will be under compression. Resultant stress will be compression. Okay. And this kind of dislocation is called as edge dislocation. So, this we call as, so this edge basically an extra row of atoms. So, if you have a row, if you have a extra row present on the top plane, it is called as positive edge dislocation. If it is present in the other side, it is called as a negative edge dislocation. Now, this edge dislocation moves as a function of stress in the material. So, when you apply stress, the dislocation can move in this or this direction. Okay. So, the way it happens is that this is the plane on which it moves and it can move. So, this can eventually, so this row will eventually move out to this point, then to this point, then to this point. So, eventually what will happen is that these atoms will come here and the one on the side will disappear. So, it will create a step on the surface, and this is how basically deformation in materials happens, by movement of dislocations in material. That is how they deform. So, when you apply stress, it will move to right or left side depending upon that stress, and it will create deformation in the materials. So, you can represent this material, this edge dislocation, by a grid kind of factor and quantify it. So, let us say this is the perfect grid of a material, 2, 3, 4 and 5, 1, 2, this is the perfect grid. Okay. You have atoms sitting at the corners there. So, let us say you start from this point, this is point A, okay. Go one step up there, another step, you go one step here, one step here, one step here, one step here, this is A, B, C, 3 steps down, D, and then 3 steps left, 4 steps left, you go to again A. This is a perfect lattice. If you have a edge dislocation, what will happen is that you will have slight distortion. Okay. So, you have one, so let us say somewhere in between you have one row there. Okay. So, I had 5, 6 columns there, 1, 2, 3, 4, 1, 2, 3, 4, 5. So, let us say I have created one extra one there. Let us get rid of this. Okay. And then we have this thing here, 1, 2. So, now if we again do this circuit, this is called as Burgers circuit. Okay. So, we start from this point. So, this is called as Burgers circuit. So, this is perfect lattice. In an imperfect lattice, you again start from point A, go one step up, another step, reach point B, 1 step, 2 step, 3 step, 4 step, you have to go to this point now. This is the point B, let us say, you had 4 steps, right. So, let us, and then you come to 3 steps down to point C, and then you reach this point to reach point. So, this is C, D, and you do not reach A, rather you reach another point A prime. This is one extra step. This is called as the Burgers vector of a edge dislocation. all right, and this Burgess vector is perpendicular to the, so this is your dislocation. So if you look at dislocation now, if I draw the 3D diagram, so this is your 3D diagram. So this is your extra step that has formed somewhere here, okay. This is your extra step, and this will be your otherwise back side of the crystal, okay. So this extra step is the Burgess vector, and your dislocation line is somewhere running like this in this direction, okay. So this is your dislocation line which is running in like this. So this is your extra plane of atoms. So this is, so basically Burgess vector is perpendicular to the dislocation line in case of edge dislocation, okay. So this is positive edge dislocation, this is the Burgess vector. So B is perpendicular to T, which is called as dislocation line. So if you draw the plane, the planar view is like this. If you look at the top view, this is dislocation line T, and this is the Burgess vector B, okay. The second dislocation which is present in materials is called as screw dislocation. And this is basically formed by shearing, okay. So this is formed by shear action, as if you have a shear action in the material. So for this I need to take help of illustration. So this was the edge dislocation. We had a Burgess circuit which showed the extra step in the Burgess in the circuit. The screw dislocation, you have two parts of the crystal sheared in this fashion, and now when you make this circuit, let us say from MNOP, so you start from M to N 4 steps, N to O 4 steps, and you have P to M, you take an extra step here. This is an extra step, and this is sheared with respect to this point. So this point, if you now draw this point somewhere within the crystal, so somewhere parallelly you will have a line like that. So here this is B vector, this is T vector. So B and T are now parallel to each other. So in this case what you had was B and T were perpendicular to each other. In this case, if you draw the top view would be like this. If I draw the side view, for example, this is the side view. This is the point of dislocation line, this is T, and your B will be in this direction as well. This is your B, okay. So this sheared region is the, so this is the step that you create, this is the line that you have, both of them are parallel to each other. So in this case B is perpendicular to T, because T is perpendicular to the board, okay. So this is T, this is B. If you look at the top view would be like this, T and B, this is an extra step B, this is B. So this is B vector, here it would be parallel. So B is parallel to T. And these are the two kinds of dislocations that we have present in the materials, and but in real life they do not exist. You do not have pure edge or pure screw. What happens in real life is what you have is a dislocation structure in which you have a mixed dislocation. So mixed dislocation, what happens is that, for example, this is a part of the crystal. So you can see on the right face of the crystal you have an extra row of atoms here. So this is the edge dislocation. So this is pure edge. On the left side you can say there is a bit of shearing, right. So this is the extra step that you form here. This is the screw dislocation, and since dislocations cannot end freely. They, since they have to close the circuit. So to close the circuit, they exist like these dislocation loops inside the material. So in the materials, real materials, you will have dislocation loops. So depending upon whether it's a right-handed screw or left-handed, so screws are defined, edges are described as, so here for example it's a positive edge, right? On the other side it would be negative edge. Here it's right-handed screw and here it would be left-handed screw, and you can see that the dislocation line in this case is in this direction and your B is in this direction. So B and T are perpendicular in both the configurations. In these cases this is your T, this is the B. In this case this is the T, this is B. Here this is T, this is B. Here this is T and the one in the center is the B. So you can see that there is a relationship, that the relationship between B and T is honored. Okay. So this is the these are the dislocations in the materials which are called as line dislocations, and the energy of these dislocations are characterized by parameter called as so dislocations are characterized by parameter called as Burgess vector, which is B. Basically it is related to lattice parameters. Okay. So for example in a FCC material, B is equal to half of 110, or you can say half of 110 type of direction, A by 2 110. So the length of B would be equal to A divided by root 2. For a BCC material it would be A divided by A111 divided by 2. Okay. So this would be equal to A root 3 divided by 2. Okay. So this is how you calculate the Burgess vector lengths. That these dislocations have energy as well. So energy of dislocations is called as is expressed as half of GB square. So G is the shear modulus and B is the magnitude of the Burgess vector. Okay. So this is how you analyze dislocations in the material. These are all 1D defects, and now in the next class what we will do is that we will look at the dislocation, we will look at the third category of defects which are called as 2D defects, which are basically surfaces. Okay. So this we discuss in the next lecture, which is the final lecture of this course. And these dislocations, let me tell you, these dislocations in the materials, they move out of the crystal when you apply stress. So for example in this case, when you apply stress in this direction, tau, this extra row of atoms will move out the, so the movement, the stress will, now look at the relation between stress, line vector and the Burgess vector. Tau is parallel to B and tau is perpendicular to T. If you look at the screw dislocation case, it is other way around. In case of screw dislocation, if you want to now apply the shear stress, now so the stress has to be applied in this direction, this is the stress axis. So stress is parallel to Burgess vector and stress is perpendicular to the, is also parallel to the dislocation line. So as you apply the stress, this direction will move in this line will move to the edge of the crystal, so that it will create a complete step at the end of it. So at the end of it, you will have all the bonds broken and you will have complete step created. So the movement of dislocation line will happen in the direction perpendicular to the applied stress. whereas in this case the movement of dislocation line will, in case of edge dislocation, so this, as you apply stress tau, the line will also move in the same direction. In this case, as you apply stress, the line will move in this direction. Okay. So the movements are opposite in case of edge and screw dislocation with respect to the applied stress direction. So with this, I think this is enough for this course. We will discuss now the surface defects in the next lecture.